My name is Allan Schweitz. I'm part of the big data team within OSS Cube. OSS Cube is basically an open source based company, originally focused on PHP and MySQL, and just since last year we started a big data practice, and we partnered with Cloudera. And we also deliver courses on Hadoop within India and in the Asia Pacific region. Last Friday we had the first part. For those who joined us, we had the first part of Hadoop Essentials, where we basically discussed where Hadoop came from. We discussed the traditional way of dealing with distributed computing and the issues that people were facing around the turn of the century, when, for instance, Google started their company, and some other online companies that had to deal with big data. And so some new requirements came around in dealing with distributed computing, dealing with large amount of data. And so this is basically where Hadoop came from, and these were some of the aspects that we touched upon in the last seminar, and a little bit of a high-level overview of what Hadoop is all about. So in this part, we go a little bit deeper on it, just to manage expectations. These webinars are mainly focused on people who's more or less new to data, new to Hadoop, and if you already do some programming or in some projects, I'm not sure if this sort of will bring anything new. So it just is focused to give people who are sort of new to big data and Hadoop a bit of a taster of what Hadoop is like and how it's sort of built up and the problems it tries to solve. Yeah, so let's get started. So this is about the basic concepts of Hadoop. Yeah. So what is Hadoop? Essentially, Hadoop is comprised of two core components. The first component is what we call the Hadoop Distributed File System, or HDFS. Yeah? So this is the file system on which all the data will sit. It is that uses multiple nodes in your distributed cluster, and all those files that you upload into Hadoop will be distributed across those nodes. Yeah? So everything else which you utilize on Hadoop is sort of utilizing this distributed file system. And we go a little bit into deeper on how this distributed file system is actually implemented. Because if you think of it, if you take, for instance, a single computer, there is a limit to a single computer in how much data you can store. Yeah? It's limited by many things. It's limited by the size of your disks. If you can imagine that, I think the current size of the hard disk nowadays are a few terabytes maybe. But nowadays companies, they sort of work with petabytes of data. So you need to find a way to be able to cope with these huge amounts of data. Then the second component of Hadoop is what we call the MapReduce software framework. Now, MapReduce is a framework that allows developers to very simply, very easily utilize the Hadoop cluster to process this large amount of data that sits on the HDFS to process that in a parallel way, yeah, without the developer having much to think about all these sort of nitty-gritty distributed problems you traditionally have. Like in the olden days, sounds like ages ago, but in the olden days when you implement distributed computing, you had to do all the programming yourself. You had to take care of distributing your data and your program. You had to take care of the communications between all the different nodes. You had to take care of checking and monitoring if a node failed or went down. So all the plumbing, generally, you had to take care of yourself. Within Hadoop, the whole MapReduce framework and the whole distributed file system just takes all the plumbing away from you, yeah? And so the developers can then only focus on the business logic. That's what they really need to do rather than all the plumbing around. So this is what the Hadoop sort of provides you. Now, on top of Hadoop, there are many other projects. There's a whole ecosystem built around Hadoop. If you go to Apache, you can see a whole list of them. But not only on Apache, if you go to GitHub or even on the Google sites, there are a lot of projects that are built on top of Hadoop. Just to give you a flavor of some of these projects, Pig and Hive, these are some high-level projects which allow you to access the data that sits on Hadoop in a very easy manner. Hive does that through SQL, so if you install Hive on top of Hadoop, you can access your data with simple SQL queries. Yeah, so you don't really even have to know anything about the whole MapReduce software. You just install Hive, and through simple SQL language, you can access the data. And Pig, in a similar way, it's a sort of a scripting language, a data flow scripting language, which allows you to process the data that sits on Hadoop. HBase is, again, it's a column-based database, which is sort of built to handle really huge amounts of data. Then we have Flume. Flume is again another project which sort of allows you to sort of gather lots of data that is being produced by different systems and inject them into Hadoop. For example, if you have like 10 or 20 websites, web servers running, and they all produce massive log files, and these log files need to be, from time to time, injected into Hadoop, then Flume allows you to do that. Uzi, another interesting project which allows you to develop some workflow-related systems on top of Hadoop. It sort of can kick off MapReduce processes, MapReduce jobs sequentially or in parallel, or it can schedule them and trigger them based on events. So all this workflow related logic you can implement using Uzi. And then Scoop, again, another project which allows you to sort of copy or import and export data from a relational database to Hadoop and the other way around. Yeah. So these are sort of some of the projects that are quite popular currently that are built on top of Hadoop. And there are quite a few more, so these are not the only ones. So when we talk about Hadoop, we can talk about many things, yeah? But at the lowest level, basically you have what we call the Hadoop cluster, yeah? And so this is basically a set of individual machines known as nodes, or we call them data nodes or slave nodes. Yeah, and these nodes, this is where all the data sits. This is where the processing takes place, and you can have a one node cluster, which we call the pseudo-distributed node. So basically, you tell Hadoop everything is just on one computer, but you can easily scale out to many thousands of nodes. Yeah, a cluster of 10,000 or more nodes is not uncommon, and the whole benefit of Hadoop is that you can scale out sequentially and scale out linearly. Basically meaning that if you add twice as much of nodes, you'll get twice more storage, you get twice more processing power. Yeah. So this is what the whole cluster is all about. So the first component, which I mentioned before, is HDFS. So this component of Hadoop takes responsibility for storing the data in the cluster. Now this needs to be done in a very special way because of the different requirements. Some of the requirements we discussed in the previous webinar was that if, for instance, a node goes down, it is not acceptable if there is any data loss. Yeah, it is not acceptable when a hard disk fails that you lose the data. Yeah, so there needs to be some internal redundancy within the whole file system that caters for hardware failure. Yeah. So the way Hadoop does this is that if you store a file into the Hadoop file system, it will chop that file up into blocks. Yeah. So say, for instance, if you have a 1 gigabyte file and I push it into the Hadoop file system, it will then chop it up in smaller blocks. Generally, the size of these blocks vary between 64 megabytes and 128, depending on the configurations, and it then sort of distributes these different blocks across the cluster and store them on different nodes. But not only that, each block is replicated 3 times. So if, for instance, one node fails, yeah, and a certain block was residing on that node, then Hadoop can then sort of find another node on which that same block resides and then engages that node into the job you're running. So the data will not be lost. So in a sense, you have also a sort of backup system, so you can ensure that even in case of hardware failure, your data will sit somewhere else on the cluster. So this sort of ensures the reliability and availability of the data within the cluster. So inherently, automatically, you have backup, and you can be rest assured that even with failure, the data will still be there somewhere on the cluster. So the next part of the next component of MapReduce is, the next component is MapReduce. So what this does, it is a framework that sort of split into 2 processes, 2 phases if you like. Yeah, and the first phase is called the map phase. Now each map phase is a process in itself. Yeah, and the map phase operates typically on a single block. Remember in the previous slides when I said that the data was chopped up in different blocks which sit on different computers, different nodes in the cluster? Now the map phase will typically sort of work on one such a block. So if I have my 1 gigabyte file which is chopped up in 7 blocks, yeah, then I will have 7 map tasks running on each blocks, all on different nodes. Yeah. So in parallel, I have 7 map tasks running on a block of data which is 64 to 120 megabytes large. Yeah, in parallel. So in this way, I can very fast process this 1 gigabyte file in parallel. Yeah. And so once all these mappers, as we call them, these map tasks, once all of them has finished, yeah, they sort of have some data as output, and that's when the reduce phase reduce phase will take place, which then sort of process the data which is sort of collected or generated by these mapper tasks. We will come to how this works a little bit later on in a bit more detail. So to come back to the HDFS discuss this for those who joined last week. HDFS sort of evolved from Google GFS. So in early of 2000, Google basically they published a paper on GFS, which sort of described a way of dealing with this problem of large files and huge amount of data, because obviously Google was growing very, very rapidly. They were gathering huge amounts of data, and they needed to find a way to deal with this. And so they published a paper on how they did this, and this is the GFS, the Google file system. And so there was this guy called Doug Cutting who was working on one of the Apache projects, Notch, who sort of had the same problem, and he was searching the internet and looking for a solution when he came across this paper. And this is when he decided to implement the concepts that were laid out in this paper, and this is how Hadoop started. Yeah, and so the way Hadoop works is Hadoop is built in Java. Yeah, it is a completely Java system, which sits on your normal operating system and utilizes your normal file system. Yeah, it's mainly currently mainly supported by Linux file systems and some Unix file systems. And so it just utilizes your normal operating system and native file system. And the whole idea of Hadoop is to sort of be able to create a huge cluster of many nodes. And obviously, if you want to create this huge cluster, it's going to be very, very expensive if you use only expensive hardware. So the aim is to use cheap, quote-unquote, unreliable computers to grow your cluster. Because in this way, you can easily extend your cluster with little investment. Yeah. If you need a little bit more storage, a little bit more processing power, you can just add a cheap node, a cheap server to your cluster. And typically the price of these servers will be somewhere between $2,000 and $4,000. Yeah. And that way you can grow the cluster as needed. So if you, for instance, are a startup and in the beginning you have very little data, obviously you don't want to start out with a huge cluster immediately. You want to grow the cluster as more data gets produced. So generally, if you think about it, that some of these online companies like eBay, Facebook, their data grows continuously. And they generally have an idea on how much data or how much processing power, how these requirements grow month by month. And so they can plan ahead that, okay, we need a terabyte of data. Our data grows by a terabyte each month. Then you know, okay, for a terabyte, I need maybe two servers each month. And then every month, I can add 2 servers to my cluster, and so gradually grow as the need grows. Yeah? And so this is the real power, the real benefit of Hadoop, is you don't have to have a lot of money to create a cluster, and you can just grow it as needed, and it grows linearly, so in a straight line. Now, Hadoop generally sort of performs best on large files. Yeah. If you want to really utilize Hadoop, it's best to sort of store big files on Hadoop rather than a lot of small files which are 1 megabyte, 2 megabytes, or even smaller. Yeah, you really want to store files that are typically 100 megabytes or larger, or preferably a gigabyte or larger. Yeah, because then Hadoop really shines. And there are reasons for it, which I will sort of reference later. So typically, you want to have large files, a small portion of large files rather than a large portion of small files. And if you have all these small files, it may be worth sort of thinking about it, say, okay, maybe we can concatenate them, put them all together in one single file, and then store them in Hadoop. Another thing you want to keep in mind that is Hadoop is sort of designed for performance. Because you have this huge amount of data, you need to be you don't want to wait hours and hours for a job to run or some analytics to be done. So Hadoop is really optimized for performance in the sense that you want to really quickly read the data very fast. You want to do it in parallel. Okay. And so in order to gain this performance, one of the design decisions that they have made early on is that HDFS is write once. Yeah. So you write the file to the file system. And so the benefit of that is you don't have to worry about all this other overhead that takes place of locking the file system and somebody edits it and rewriting it and all of these things. Yeah. So once it's written on HDFS, it's read-only and you can only read it. You don't have to worry about concurrency and all of these sort of things. So that was one of the early on design decisions they made when implementing HDFS. And so therefore, Hadoop is really, really fast in reading because it doesn't have all this extra overhead. And secondly, it is sort of optimized for streaming. And this is one of the things that I was mentioning for the small files is you don't want random reads. Because one of the issues with random reads is that you have a lot of seek time. The disk will need a lot of seek time to locate the data you want to read. Rather, if you have one sequential file you want to read, the disk can just scan through it very, very quickly and just read the data all at once. Yeah? And so this is why we also want large files. If you have lots of small files, yeah, and they're scattered around, and you want to process those files, each time you finish one file, so you need to go and seek another file and seek another file. So there will be a lot of seeking time there, and it will take a bit more time for Hadoop to sort of actually read the data that are in these different files. Yeah, that's one of the things. There are another issue with smaller files, which I'll address later. Yeah. And so how are these files stored? Like I mentioned before, they are split up into blocks, typically 64 megabytes to 128 megabytes large. And each copy of each block is then copied to a node. and then distribute it across the different nodes, and each copy of the block is sort of replicated 3 times on different nodes. So if one node goes down, you will be assured that the data that's on that node sits somewhere else within the cluster. So Hadoop, if one node goes down and you needed some data, then Hadoop can automatically find that data on one or another node within the cluster. So you don't have to worry about backup and restore and all of these sort of things. And again, it's not something you have to do explicitly and take care of, all of that. This is all comes inherently to Hadoop. If you have a cluster, automatically everything will be redundant. Yeah. The other benefit is that the data is distributed across many machines. So processing this data becomes more efficient. One of the examples I gave last week in the first part is that the traditional way of distributed computing is you sort of copy the data to the processing power, you process the data, and a result set comes out. Yeah. Now, that was easy in the early days because back then they didn't work with that much data and processing power was more important. But nowadays data becomes more important than processing power, and the amounts of data that need to be processed are becoming huge, and you can't just ship a petabyte of data to one computer and tell this computer go and process this. Yeah. So a new sort of way of processing this data needed to be found. And the way this is done is by distributing this data across your cluster, chop it up in small blocks, and what you do is you send your little program to those nodes and say, go and process where the data sits. Yeah? And these little programs, the MapReduce jobs, they're just small files, generally a few megabytes large, depending on your implementation, which you then copy to the node, and there you say, okay, go and process the data where it sits. Yeah. So this is one of the concepts. This is basically how Hadoop works underneath. Now, the way sort of, like I said, if for instance one node goes down, you need to find the data on another node. Yeah, because one node is not available and the data that was on that node is no longer accessible. So you need to find another node where the data sits. Now, within the Hadoop cluster, there is a special node which we call the name node. It's a master node. Yeah, and so basically it is the name node that sort of keeps track of where your data sits. Yeah, it sort of keeps tracks in how many blocks your file is split and on which nodes each block sit. Yeah, so this name node basically keeps track of all the metadata. So if you want to sort of find out where a file sits, yeah, then basically what Hadoop does, it queries the name node, and the name node says, okay, this file is split up in 7 blocks, and block 1 sits on that node, block 2 sits on that node, block 3 sits on the other node, etc. This is what the name node does. Yeah. Now, if you want to sort of access the data, there is the Hadoop API which you can utilize to access the data. But there is also, by default, when you install Hadoop, you get the Hadoop client. And with this Hadoop client, you can then access that data on your Hadoop file system. Yeah, so this is an example, what you see here, of how that client works. The client, you type in the command Hadoop, You say, okay, I want to access the file system FS, and then you can say, okay, I want to copy from my local system to a folder in HDFS. And it will then sort of upload all the data that sits on your local machine into HDFS. And the other way around, Hadoop FS, you can copy data from HDFS to your local computer. You can do quite a few standard file system operation, like you can do ls to list all the files in your folders. You can do cut, where you can say you can view the contents of a file that sits within Hadoop. All these sort of things you can do. You can do move, you can do a copy, you can do a make dir. All these standard file system operations you can do on HDFS using the Hadoop client. Alternatively, if you're a little bit lazy, you can install Fuse DFS. And Fuse, I'm not sure, for those who are familiar with Linux or Unix operating systems, Fuse is sort of an interface which if you implement it correctly, it allows you to use standard file system commands on the interface you've implemented. So Fuse DFS is implemented for Hadoop, and so if you can then mount the Hadoop file system as a normal file system on your local on a local folder, and then you can do the normal file system commands. Obviously, with some of the limitations, you cannot update or modify a file because Hadoop is read-only. So just an overview of some ecosystem projects. Flume, like I already said, it allows you to sort of copy data from sources into Hadoop. A normal use case is log files from your web servers. Scoop can sort of copy data in and out from Hadoop into RDBMS and the other way around. Yeah. And generally you will see a Hadoop sort of, currently Hadoop is used a lot of in conjunction with business intelligence tools, something I also sort of used some POCs for some clients, is where you say, okay, currently the data warehouses and all these BI tools, they really can't cope with this huge amount of data, and generally you will also see they don't need this huge amount of data, but the relevant data needs to be sort of filtered out or from this huge amount of data, and this is where Hadoop ideally comes in, where you say, okay, Hadoop sort of crunches through these petabytes of data, outputs only the relevant data, and pushes it into a data warehouse where then all these BI tools can work. So this is a typical use case of Hadoop in organizations. Now, to come back to sort of how the whole cluster works and the HDFS, this is a good example of that. So in this example, we have like 7 nodes. Yeah, the darker blue node is the name node, which is a master node. So we have master nodes and we have slave nodes. Yeah, and so the name node is a master node, and the data nodes are slave nodes. Yeah, generally data nodes are very, very cheap hardware. Yeah, you don't want to spend a lot of money on slave nodes. Yeah, they are expendable. If they go down, they don't harm the cluster. You just replace them with another node. Yeah, and so you don't want to spend a lot of money on those. However, the master nodes, they are critical to your cluster. So the master nodes, they need to be running. If the master node is down, in some cases, in case of the name node, if the name node goes down, then your whole cluster becomes inaccessible. Yeah, you can't do anything with your cluster. So in this case, the name node is a single point of failure. So in this case, you do want to spend some money on sort of more reliable, more quality, more high-end hardware. Yeah, and you want to take some precautions that if the name node goes down, something else, there is some backup or some restore facility there. Yeah. However, for the data nodes, you don't have to worry about that. If a data node fails, you just throw the computer away, plug in another one, or you repair it and rejoin it to the cluster. Yeah. So the name node holds all the metadata, and you can see that if the metadata is gone, if you try to query the cluster, you can't query because you don't know where the data sits. All this metadata is stored in the name node. So in this example, we have two files. We have a file called foo, and we have a file called bar. And in case of foo, the file is split up into 3 chunks. Yeah, chunk 1, chunk 2, and chunk 4. And each chunk is then replicated across 3 nodes. Yeah. So if I look at chunk 1, we can see it sits on the upper left node, in the top middle, and in the bottom left node. Yeah. So that little chunk is replicated across 3 different nodes. And the same applies to the other 3 chunks. So if one node goes down, like for instance, if the top left node goes down, I can always find my chunk 1 in 2 other places. Yeah? And so I will not lose any data in this case if one of these nodes go down. So this is basically the concept how HDFS works. So if I sort of want to access a file on HDFS, say using my client tool, the way it generally works is say, okay, I want to get a file foo. Yeah? So copy file foo to local system. So what my client then does, it goes to the name node and queries and say, okay, do you have file foo? The name node says, yep, I have file foo. And it's split up in 3 chunks, in 3 blocks. And you have block 1, block 2, and block 4. And you can find this block on node 1, node 3, and node 4. Yeah? And so the client then goes to these nodes and then retrieves this data, puts them all together, and voila, I have my foo file. Yeah? So this is basically what happens behind the scenes if I sort of query a file. This is basically what I just described before. It just shows you have the client. It asks the name node, okay, can you find me file bar? And then it says, yep, you need 3 blocks, and they're sitting on these nodes. And then the client goes directly to the nodes, retrieves the data, and then puts them all together into one single file. And you can then access that file as if it's a normal file. Simple, right? All right, so that was the whole Hadoop file system. Now we have the MapReduce. So we have all these files. Yeah. We have all these files, and I've seen there coming in quite a few questions. But if everybody's okay, I'll just answer these questions at the end. So the next part is the MapReduce job. Yeah. So basically what happens is you want to process this large data which sits on different nodes. Yeah. And so what happens is, in order to be able to utilize this huge cluster where you have all these different nodes, is that you want to process that data that sits on certain nodes. So where the data sits, that's where you want the processing to take place. Rather, you have one central computer and move all the data to that central computer where the processing takes place. You say, nope, the computing logic, we move that to the data nodes, and that's where the processing takes place. Yeah. So if I have my nodes, say for instance, if I go back one slide, yeah, I can see here that I have my data sitting on different nodes. Then my processing program is then distributed on those nodes where this data is located. And it then starts processing, doing the processing there. Yeah. And the benefit of this is I can do this massively in parallel, especially if I have a huge amount, very large file which is distributed across many nodes. I can just process that data completely in parallel, very quickly, and each process just processes a very small chunk of data, which is 64 megabytes to 128 megabytes large. Yeah, so all these little programs running on different computers, running a small chunk, processing a small chunk of data is obviously much more faster than you will have one process trying to process this huge file, which can be gigabytes, 100 gigabytes large even. Yeah, and so this is the idea. So we process the data where it's stored as much as possible. Now within MapReduce, we have two phases, like I said before, the map phase and the reduce phase. Yeah. So, and we'll come to that a bit later. There will be a diagram and how these phases work. Yeah. But the MapReduce framework, like I said, it allows you automatic parallelization, yeah, and distribution. So in the case of foobar, if you say, okay, I want to process the bar file, you say to Hadoop, okay, this is my little program that processes the bar file. I submit it to Hadoop. Hadoop then finds out, okay, where does the data for the bar file sit? Oh, it sits on nodes A and C. What Hadoop then does is copy my little program. It copies it to node A and node C, and this little program then starts running in parallel on those two nodes. This is the real power of Hadoop. And there is even some fault tolerance in there, saying, okay, if say I'm running my little job on node A and node C, but for some reason, whilst running that job, node C fails, yeah, then Hadoop says, oh, oops, node C fails. Okay, where is the data for, is there another node where the data for the bar file sits? Yep, it's on node D. Okay, submit the job again, but this time on node D, and start processing again. So in this way, even if you have a job running on certain nodes and that node fails, Hadoop can deal with that. Yeah, there's some internal monitoring, status checking, checking the health of each node, and it will sort of adjust accordingly. Yeah. And like I said before, the whole MapReduce framework is really focused to allow developers to only focus on business logic. You don't have to do all that plumbing underneath, where you need to sort of cater for the communication, the parallelization, the distribution, the fault tolerance. You don't have to think about that at all. You just focus on the business logic, and Hadoop takes care of it. And so Hadoop allows you in a much easier way to create programs that run distributed across your cluster, working on large sets of data, which was a lot of work before. So to go a bit into the more detail for how this whole MapReduce framework works, everything within MapReduce is based on key-value pairs. Yeah, so it reads the data in key-value pairs and it outputs the data in key-value pairs. That's how it works. Very simple. To give you an example, for those who sort of don't understand what I mean by key-value pair, say for instance, if I have a log file, yeah, that is a very common example, a log file for my Apache web server, yeah. So in this case, I want to process my log files from my web server, yeah, and the way generally this log files look like is you have a file, and within that file, each line represents a log entry of your Apache web server. Typically, it's a hit. It says, okay, a user with this source IP address access this file, the size of the file, the browser agent, and some extra data. Yeah, this is typically what a log entry looks like in the Apache log files. Yeah. Now, if you want to sort of process these files within Hadoop, then the key in this case is for instance, the line number in your file. So you have log entry 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 is in this case is then the key, and the value is the whole line, yeah, which says, okay, source IP address, the file, the HTML file access, the browser user agent, and all of this stuff. Yeah, so the whole bit there is then the value. Yeah, and what the mapper then does, it reads through this log file line by line and allows you to process each line. Yeah. So if you want to sort of find out which file is accessed the most, which page on your website is accessed the most, you need to go and parse that line and filter out all the HTML files or the pages and then count each page how many times they've been hit. Yeah? So this is a typical way of how Hadoop works and how you can utilize Hadoop to process your web server log files. Like I said, everything is in key-value pairs. You don't have to do anything with the key. In this case of the log files, you're absolutely not interested in the line number. You're just purely interested in the log entry. So you can ignore the key. The example here, they have a word count. I'll just go quickly through it because we don't have that much time to sort of go in detail. But the way it works, again, if you want to sort of count how often certain words appear in your documents, yeah, so the way to do that is, again, the documents are like the website log file. You have a line, every time a single line, yeah, and you need to go through these lines. So the input would be, again, your line number and then the line in your file. So in this case, we have two sample lines that are being read, the cat sat on the mat, the aardvark sat on the sofa. So those two lines are read, and you can have many, many more lines, and you want to then count how often certain words come. Now, what the mapper does, it goes through these lines, yeah? So it processes one line, and for each line, the value is this whole line, the cat sat on the mat. That is the value. The key here is 3014. We just ignore the key and just focus on the value. And then what we do is we just output the word as the key again, yeah, and just give it a number 1. Say, okay, I've encountered it once, yeah. Then we go to cat. Okay, output will be a new key value pair, which says where cat becomes the key and the value becomes 1. And so we go on and iterate through all the lines and do these same things. Yeah, this is what the mapper does. So it produces a whole list of key value pairs. Now this is output, so here you see sort of a bit nicer form on how it looks. Yeah, this is basically the same as what you see here. Yeah, and so basically what happens is the output then goes into the reducer. Yeah, so the map face processes all this data, finds all these words, splits the lines up in different words, gives them a value 1, and this I then output into a big list. This list is then given to the reducer. Yeah, there may be one reducer, there may be multiple reducers, but these reducers generally sit on other computers. So the output of the data output of the mapper is then copied across the cluster to the nodes where the data sits, where the reducer sits. Yeah. In some cases, Hadoop will be very clever that some reducers will sit on the same node where a lot of data sits, so you don't have to copy the data across the network. And also, when you're programming, you want to try and minimize the data output of your mapper. And so that is copied across the reducers. Those lists are sort of spread across multiple reducers if you have multiple reducers. So these reducers can then start processing the output of the mappers in parallel, yeah? And then the output will give you a count of all the words, yeah? So the output can be 0 or it can be more. So how does it look like in this case? Yeah. So from the output of the mapper comes into the reduce phase. As you can see on the right, the blocks, yeah. So artifact 1 goes into the reducer, yeah. And then, so basically, you can start doing the count. And so the output of the reducer will then be, okay, I've encountered artifact once, cat once, but on I have counted 4 times, set I've counted 2 times, and for instance, I have counted 4 times. Yeah. So this is basically in a sort of nutshell how sort of MapReduce works. Map processes data, outputs key value pairs. There is a phase in between where when the output of the mapper gets sort of sorted, all keys are combined together and then fed into the reducers, and the reducer then actually does the counting. This is a little bit, a lot of people have a bit difficulty in sort of trying to sort of understand this concept, because a lot of people have the traditional database background where you think in a relational concept, where you think in querying, SQL queries, select star from a table. This is completely different, yeah? This is absolutely different. You need to sort of change your mindset in how Hadoop works internally. So the overview here, you get the input, you have 2 lines that come in. The mapper then sort of reads these lines, creates this key value pair in the middle. Yeah. Then a shuffling takes place, which is automatically done. You don't have to do any programming for that. The programming that the developer does is the mapping bit and the reducing bit. Yeah, and so the shuffling takes place where all the keys are combined into a single key value pair, and then sent into the reducer, and the reducer then does the counting. Yeah? This is a very, very simple overview of how the whole MapReduce framework works together. So yeah, this is the word count example. So we want to understand how often words appear in certain documents. Also, it is for some analytics, it is quite important because you want to see which words are important, how, in which context people use these words, all of these sort of things. Yeah, especially in the in the advertising industry, this is quite an interesting use case, because obviously you want to sort of find out which words are attractive for you, which you want to use as keywords for your advertising. So these are sort of basically the way MapReduce works. The whole idea is just to split the data up in small chunks and let it work on small tasks distributed across your cluster. You can do a lot of things that you are used to within the relational database, like max, min, sum, count. All of these things are possible, but obviously you need to programming, and it's a little bit more work than you're used to if you're using simple SQL queries. But again, that's why these other projects like PIC and Hive are created to make this whole bit of programming a MapReduce job much, much more simpler. Yeah. So the last bit about the cluster, how it is. Obviously, we from OSS Cube, we've partnered with Cloudera. There are a few other Hadoop vendors out there as well, but Cloudera offers a sort of for system administration. We offer different courses, but they have also different tools around the whole Hadoop that allows you for easy administration. And these tools you can download for free. The administration tool, I know it is for free up to 50 nodes in your cluster, which is quite already a quite noticeable size cluster. So feel free to download and play with it. Within the Hadoop cluster, there are sort of 5 main components. Yeah. We've already touched upon 2 of them, which was the name node, which holds all your metadata, which is your central, basically your single point of failure. Then we have a secondary name node. The secondary name node is a bit of a confusing name because it's not a backup name node. It just does some housekeeping functions. Yeah, it's not like if the name node goes down that the secondary name node takes over. It's nothing like that. It's just for some housekeeping functions. Then we have the data node. This is where is a slave node where all the actual data sits. Then we have the job tracker. Again, the job tracker is a master node. Yeah, so the job tracker basically keeps track of all the MapReduce jobs that are running on your cluster. So if you create a new job that you want to run on your cluster, you basically submit that job to the job tracker. Yeah, and the job tracker then keeps track of all the jobs running, the status, and all of these sort of things. Again, this is a master node. However, if the job tracker goes down, the cluster will still be alive as such that HDFS will still be running, but if the job tracker is down, you cannot run any MapReduce jobs. Again, so this is a single point of failure from the point of view of running your jobs. Yeah, but you can still access the data. And then you have a task tracker. Again, a task tracker runs on a slave node. typically it runs on a data node, yeah, where it's sort of, when you have your job tracker, you submit your job to the job tracker. The job then submits your job to all these different data nodes, which then sort of get submitted to the task tracker, and the task tracker then executes this job for you locally on that node. And it keeps does some monitoring and some health checks and all of these sort of things, and then sort of feeds back information to the job tracker, so the job tracker knows the status of the overall job. Yeah. So this is how a typical cluster configuration looks like. You have your master node. On the master node can be both the name node and the job tracker. But if your cluster grows larger, you typically want to split them out into different servers. Yeah, so one server for your name node and one server for your job tracker for performance reasons. Yeah. So if you have your job, so your developer has written a nice new job to process some data, that gets submitted by the client to the job tracker. The job tracker then finds out, okay, which data does this job need in order to execute. It finds out where the data sits, yeah, and then copies this job, this program, to all those nodes where the data sits, yeah, and submits it to the task tracker on that node. The task tracker then executes the job. First executes the mapper bit, yeah, and once the mappers have finished, then the reduce bits gets executed. And the output of your MapReduce job then gets written back on the HDFS file system, on the cluster. Yeah. So once your MapReduce job is done, you can then go into HDFS and look up the output of your MapReduce job. Yeah. So what you need to think about when you set up a cluster, like I said, there are some single points of failures. These are generally the master nodes that are single point of failures. Currently, there is no out-of-the-box support yet for automatic failover and all of that, but they're working hard on it. If you want the automatic failover, it is something you as an administrator need to take care of yourself, that you have some sort of, how would you say, mirroring system in place that you need to implement yourself in order to mitigate these risks. But in future releases of Hadoop, more and more of these pain points will be sort of resolved. Yeah. So for now, for your single point of failures, the suggestion is just that you put in more expensive hardware, more extensive monitoring, and maybe create hot standbys. Yeah. So that's it for now, which sort of covers a bit more into detail of the concepts of Hadoop. Yeah. And so if you have any questions, you can always email us. I will try and answer a few of the questions now, if you have it. Okay, so I'll just go through the questions that are already there. Okay, one of the questions is what is the prerequisite for learning Hadoop? Any programming language? Good question. Hadoop basically is implemented using Java. Yeah, and so it's really optimized for Java, and the whole APIs is implemented in Java. So it would be a very good advantage for you if you have any Java background in developing Hadoop jobs. However, having said that, the API is such that it really limits you. You don't need to know too much of it. So even if you have non-Java skills, the learning curve is relatively sort of low. Yeah, it is not very steep. The other thing is that within Hadoop there's something that they call the streaming API. Yeah. So the streaming API, what it allows you to do is it allows you to say, okay, Hadoop reads the data for you and sort of pipes that data into your program, which is written in your language of choice. For instance, if you do it in Python, or if you want to do it in Perl or some other script, yeah, which you are more familiar with, you can use that. Yeah. So when you submit your job, all you have to do is you tell Hadoop, okay, I'm going to submit my job, but this is my little Python program that I implemented for the map phase, and this is my little Python program that I have implemented for the reduce phase. Yeah. And there you go. So yes, you can use other programming languages as well for Hadoop, but it would be good to sort of have some Java knowledge as well. So I have a question here from Harmeet. Where do the map tasks run on? Well, the map tasks run on the data nodes where the data sits. Yeah. So when you submit your job, what basically does is it sort of finds out where the data sits, copies your program there, and that's where the map runs. All right. So the next question, can I get a link to the download Google FS paper? Yes, I think if you search Google, I have one locally on my disk somewhere. But if you just Google for Google's GFS paper, there will be a link somewhere to the PDF file. If you can't find it, please drop us an email and I'll send it to you. All right, so next question. By Sajat, and the question is, if file modification is not allowed by Hadoop, then what is the alternative for achieving it? Very good question. If you really sort of want to, have editing, you might reconsider whether Hadoop is the best option for you. If you really need updating files. The other thing is that there are some ways around it. Like for instance, if you use HBase, which utilizes the Hadoop file system, in HBase you allow to update records. And the way it does it is through versioning. And so it sort of emulates updates. And this emulation takes place by sort of appending the existing file. So you don't update the file, you just add to the system, which is a new version of the original file. And so in that way, you can emulate updates. Yeah, so hopefully that answers your question. But if you really want to direct file system access and update files, yeah, I would question whether Hadoop would be the best option for that. Cloudera distribution, can it be installed on 30-bit, 32-bit? Yes, if you have Linux. Because Hadoop is built on Java, you just need Java installed, and whether if it's a 32-bit operating system, all you need to do is basically install the 32-bit version of Java on your system, and off you go. And if you have a 64-bit system, you install the 64-bit Java on your system, and off you go. Yeah. So it's both 64 and 32 bits are supported. Is Job Tracker a kind of software program? Job Tracker is more or less a daemon, a process that runs in the background on your server, on your node. Yeah. So what happens is it's part of the whole Hadoop infrastructure. Once you install Hadoop, it will install all this software, all these daemons automatically for you. And each daemon is a separate Java program which gets started as soon as you start the cluster. Another question, a lot of questions coming in. Next question. I'll try to keep them as short as possible because we're already over time. The next question, what's the basis for key value per generation? It's a good question. Well, good question. I'm not totally understand the question, but the reason, the main reason I feel that this decision was made is because of the way Hadoop processes its data, in the sense that you want to sequentially go through all the data without loading the whole data in your memory. Yeah. So one of the things within Hadoop is to keep a small memory footprint. You don't want to load a petabyte of data in your memory. And one way of doing that is sort of processing, for instance, line by line. So in the case of this example I gave about your log files, you don't want, if you have a large log files, you don't want to load the whole log file into memory, but just one line by line. And so what it does is you give just one line and then allow Hadoop to process that line, or your MapReduce process to process that line, then the next line, then the next line, then the next line. And once you process the line, you can discard it from memory because you've already processed it. And so that is sort of the way Hadoop works. And so this line concept, processing line by line, is ideally implemented using this whole key value pair concept. So hopefully sort of that gives a bit more clarity. Will these slides be posted online? I think I have to ask my colleague for that, if that's going to happen.
So we're not really sure about that.
Okay.
But however, in case things worked out, maybe we can always get back to these people and share the link if it is really required.
All right. Okay. So if you're interested, at least email us.
Yeah.
And then we can let you know. Because officially these slides are from Cloudera, and so we need to have permission to do that. All right. Okay. I'm going to answer these few more questions, and then we call it a day. The next question, copy from local, copy to local utility, do they have any intelligence? No, they don't have any intelligence. It's just a plain copy. That's it. Nothing special. If you want to have some intelligence there, then I suggest you use either something like Scoop or Flume, or maybe some ETL system. Currently, all the ETL tools have support for Hadoop, like Talent ETL, for instance, one of the open source vendors. They have plugins for copying data to and from Hadoop with quite a bit of intelligence. Okay, next one is share a slide. We've answered that question. Would the map and reduce jobs executable and custom for each business problem? How do you tell Hadoop to use them? Sorry, I don't think I fully understand. Would the map and reduce jobs be executable and custom for each? Yeah, so generally a MapReduce job is tailored for a specific business problem. Theoretically, you can do some intelligence that one MapReduce job can sort of tackle multiple business problems. But the whole idea of MapReduce is to keep things simple and split them up in simple tasks. So my suggestion would be to keep it simple and not allow one MapReduce job tackle multiple. What you can do is you can chain a MapReduce job, so the output of one MapReduce job becomes the input for another MapReduce job. In that way, you can tackle more complex problems or multiple problems if you need. Where does name node sits, or we need to provide it? The name node is just a separate server in your cluster, yeah. And usually this is a high-end server, a bit more expensive hardware, which makes sure that it's more stable. Yeah, so it's just a server in your cluster. Theoretically, you can have all these daemons sitting on one computer, like you have one node cluster, but this is just mainly for development purposes. If you have a production cluster, you have a separate server which sits in the cluster dedicated to the name node daemon. Next question, what's the difference between Hive and HBase when both are built on top of, and how do they? Okay, so Hive basically uses standard HDFS, which allows you to query in an SQL manner. Yeah, so you need to organize your data a little bit properly, and then you can just write a query, SQL query, and what it does, it converts that query into a MapReduce job. Yeah, so the output of a Hive query is a MapReduce job. It generates a MapReduce job, which then gets submitted to the cluster. HBase basically is more similar to, I'm not sure if any of you is familiar with Google's Bigtable, but it sort of is a big tabular database which does not use SQL. Yeah, you use get and put, and it does not use the MapReduce system. It uses HDFS to make sure the data is distributed, but it has its own sort of mechanisms in order to query the data. So it's a bit of a different concept from what Hive is. Okay, next question. I have installed all Hadoop setup install, but am not able to execute queries on it. I have Sequin. It shows nothing when I show. I can see the Hive prompt. Yeah. Yeah, this would be some troubleshooting. I don't think I can solve your problem now. I need to really figure out what you've done wrong, what the actual error is. So to be honest, this is not something I can answer now. I can't tell you out of the box right now what is wrong. But the only thing I can tell you, if you installed it and you installed Hive, Hive will only work if you import some data into Hive. Yeah, so you need to tell Hive it needs to query something. If there's no data to query, then obviously you won't get any data back. So the last question, and then we call it a day. since name node is a master node, so what are the requirements like RAM, HD, etc. in terms of yeah, so the requirements basically depend on your use case, your cluster. You need to keep in mind that the name node keeps track of all your metadata, yeah? So, and where it sits. So the more clusters there are, the more nodes there are in your cluster will influence. All the metadata of the name that the name node keeps will be sort of loaded into memory. All the metadata, all its metadata. This is for performance reasons, yeah? And so whatever metadata you hold, you need to make sure that your RAM is big enough to hold it. Now, what does this size depend on? It depends on the number of nodes, yeah? And it mainly also depends on the number of files, yeah? Remember in the beginning I said that you want to be sort of you want to have less large files rather than having a lot of small files. Each file that Hadoop needs to keep track of has a memory footprint. Yeah. So if you have billions of files, then obviously you need to load the references of those files into memory. Whilst if you have only a few hundred thousands or a few millions of files, but these files are really large, then your memory footprint will be really, really small. So really, it basically depends a little bit on your use case. And again, to keep the footprint small, large files, a small number of them rather than a lot of them. Yeah. And so by this, that was the last question. I would thank you for not falling asleep. Well, I can't monitor that. And so thank you for your time. And if you have any queries about training, please email us. My colleague Rashi will be happy to answer them.
Absolutely. So guys, thank you so very much for all the time, all the patience that you had. In case of any questions, please revert us. We'll be more than happy to address you. Thank you so much. Have a good day ahead.